Okay, welcome audio diehards. We're so happy to have you here. It's great to see that more than 10 or 15 people would like to hear about high-performance audio on Android. We were running bets. So I'm Ian Nee Lewis. I'm the developer relations contact for audio. If you send audio questions to our developer support email, probably I will answer them. But today it's my great pleasure to introduce a couple of friends of mine from the engineering team, Glenn Kasten and Rafe Levien, who have actually done a huge amount of work in the last couple of years to set the standard for Android audio and make it better. And you're going to be hearing today some happy stories and some sad stories, just to prep you on that. But believe me, these guys have advanced the state of the art for Android audio more than anyone else. And also Rafe did some too. I know you're gonna call me on that. Anyway, I should stop talking. Let's go ahead and welcome Glenn Kasten to begin a high-performance audio on Android.
Hi, everyone. I'm Glenn Kasten. I'm on the Android audio team, and my job is to provide great Android audio performance. I work with our OEMs and silicon on chip vendors to help them build devices that have really great audio. And my goal is to provide you developers really top-notch audio. That's what I'm working on. I know what you want to hear, so let me disappoint you first, as Ian was hinting at. We're not quite there yet, but the good news is we are definitely making progress. So today we're going to tell you the story of what we've been doing so far and how you can take advantage of the work we've done so far. We're also going to tell you about what's coming up in the future in terms of our performance goals. Now, performance could mean a lot of different things to different people, but today we're going to focus. We're going to focus, among all these different things, on just one area, which is output latency. If you're interested in input latency or other kinds of audio performance, definitely check us out at office hours. Actually, check us out at office hours anyway, even if you're not interested in something else. We want to talk to you about the other things, but today we're just going to focus on output latency, because that's the area where we've made the most progress over the last 2 years. So with regards to latency, this is sort of a mock slide showing where we were, where we are now, and where we want to be. But it doesn't really tell the whole story of, why did it take us so long to get to this point? What's the work that's been done? What's the work ahead? What can you do as audio developers? So today we're going to really get into this in more detail. Now, explaining that is a really big job, and so I brought along my buddy Rafe, who is going to help me out.
Hi, my name is Rafe Levien, and I work on the Android Frameworks team. And you may know me, Glenn, next slide, from such features as Inconsolato, the programming font. Now, my day job, next slide, my day job is font and text rendering on Android, but in my spare time, I've been building a software emulation of the Yamaha DX7 synthesizer. I actually brought the original with me today, but I've been building a software emulation, and I really wanted the emulation to be as beautiful as the original synthesizer. And in fact, that's how I met Glenn. I was trying to figure out why I couldn't get better performance running my synth engine on Android, and Glenn's name kept popping up in email threads about audio latency. So
I fixed all of his problems.
Well, let's just tell the story. It's a good story.
When Rafe first contacted me, we were already looking into audio performance. The Android Frameworks team, the graphics team, the apps team, they were all looking into performance too, mostly on the touch side and on the graphics side, but the audio team was definitely looking into performance too. And overall, we were calling this Project Butter. We were all thinking, how can we make things more fast, more smooth? But when it came to audio, there was really only one thing that everybody knew for certain. The latency was just too darn high. No question about that.
I think I was in the same situation as a lot of you guys. I was writing a musical instrument that was supposed to be responsive, but I could hear a noticeable delay between the time I hit a key and the time my app responded. Latency is the delay as a signal passes through a system, from your app to sound. Some musicians, like organists, are trained to deal with high latencies if it's consistent, but most people are sensitive to latencies greater than about 20 milliseconds. And some can't deal with any latency at all. Any percussionists or singers here? I wasn't asking for 0 latency. I would have been happy with 10, maybe even 20 milliseconds, but I was hearing noticeable delays, over 100 milliseconds on some devices. This story is about how Glenn helped me get my app's latency down to where it became a truly playable synth. As you'll see, it took us some work on both the Android side and the app side. So as we tell the story, we're going to keep a running to-do list of things we've done, things we still need to do, and things you need to do in your app to get low latency audio to work.
Now, I know you're all dragging out your notebooks now to start writing down this to-do list, but don't worry, we are going to show the to-do list at the end also. So the first thing, the most important thing, and you're going to see this throughout the whole talk, it's going to keep coming up over and over and over again, is measure everything. We do it, and we hope you will too.
Before you can make changes to improve performance, you have to have an objective measurement of how bad it is. Otherwise, you're flying blind.
So my brother Steven was a musician, and he also built electronics. And I told him about my project working here on audio latency, and he encouraged me to get an oscilloscope. Because, let's face it, real engineers have scopes. So even though I worked at Google, I do have a budget. So I got the cheapest oscilloscope I could find. And it's definitely not anything fancy, not good for high-speed communications, but it's certainly perfectly adequate for audio.
The scope makes it possible to get precise measurements, but the really tricky part is getting accurate and reproducible measurements, especially if we want to hopefully someday make this part of the Android compatibility testing suite. We also need to make sure we isolate audio output latency from the other sources of delay in the system, like the audio input or the touch panel. Glenn came up with a cool way to do that.
So besides the scope, another great tool that I love is the Audible LED, or lighting emitting diode. I remember discovering the LED when I was 12 years old, and I've been in love ever since then. I think one of the greatest things about a phone is the notification LED. It's so useful, so fast, and yet it's really underused. I could measure audio latency with an LED, a photodiode, and an oscilloscope. Basically, you just turn on the LED at the same time as your application is outputting audio data, then measure the difference in time between when you can detect the light from the LED and when you can detect the audio signal. That difference is latency. So my brother was into electronics. I was too, especially when I was younger, so I brought back my electronics kit, and I started with a breadboard design. This is it. Later on, one of our hardware engineers, Clinton, helped me out, and he made me a real live printed circuit board, which you can see here. No, it does not actually have a red border on it. That's just a highlight. And here's the result with an oscilloscope. Basically, the yellow trace is the light detector, from the LED to the photodiode, and the blue trace is the audio. I unfortunately can't really get into exact numbers. They don't let me hear it, but let's just say that it was a really big number, way too big. So let's talk about why.
Latency Latency in the real world is complex, but in software, it generally boils down to one thing: chains of buffers.
Here's a typical unoptimized audio pipeline, the kind that I found when I first started looking at this problem a couple of years ago. As you can see from this diagram, we have 4 buffers of 1,024 frames, or 23 milliseconds each at 44 kilohertz. And that's just in the audio hardware abstraction layer, or HAL, and the kernel driver. That doesn't even count the buffers in the media server, in the DSP, in the mixer, or certainly not in the application.
In case it's not clear, that's a huge amount of buffering. There's 92 milliseconds of latency see right there. If you're an audio developer, you've got to be asking yourself, why are the buffers so big, and why are there so many of them?
So there is a technical explanation, which we're going to get into today, but I also think there's a social explanation, and we'll hint at it throughout the talk today, too, also.
Let's start with the technical. It has to do with power consumption. The larger the interval between CPU core wake-ups, the less power needed.
So as you know, mobile phones run on batteries. Batteries have limited life. So the CPU switches on and off very, very frequently between normal state and low power state. The size of each audio buffer basically puts a lower bound on the amount of time that the CPU can be asleep before it has to wake up again and process the next audio buffer. To a certain extent, that defines both your power consumption and your potential latency. And if you want to reduce power, you have to add more buffering so that the CPU doesn't have to wake up as often. As for the social component, my theory is that buffering is just a really quick and easy way to fix audio glitches. If you hear a glitch, almost always it seems that if you just make your buffers bigger, it'll make it go away. And unless you actively police buffer sizes, they're going to continue to increase over time.
And other than a devoted band of developers like you and me, it didn't seem like anyone in the Android world has had a compelling incentive to reduce buffer sizes. I think a lot of us suspected that there wasn't actually any particularly good reason for latency to be as high as it was. Maybe the buffers were just bigger than they had to be.
Sounds simple, huh? Well, this turned out to be a pretty easy hypothesis to disprove. I tried an experiment. Remember, we started with 4 buffers of 23 milliseconds each. So I just said, OK, let's make them smaller. Let's have fewer of them. Instead of 4 of 23, I went down to 2 of 12 or 13, then 2 of 6. And eventually, on one device, I was even able to get down to 2 buffers of 3 milliseconds. I didn't try to change the system architecture or anything else, just the buffers. And amazingly, it worked. Audio still played. The latency went down dramatically. I was done.
You were done? Are you sure?
Well, OK, you knew the talk wouldn't be over now, huh? It did work most of the time. But every once in a while, I heard a click, a pop, an underrun. And this really did make me sick to my stomach. I know it's hard for me to show it today, but I felt awful every time I heard those clicks. And I knew this was not going to be so easy.
And I've had a lot of experience with underruns myself. I heard them on my synthesizer when I had too many voices playing. I think it's worth talking a little bit about the methods we use to detect them.
Definitely. But first, let's listen to some underruns together. Don't worry, it's only a few seconds. But we want you to know, all of us to use the same terminology. In this clip, we're going to first hear a few shorter clicks, followed by some longer dropouts. They're all underruns. Did everybody hear those? Great, OK. We're a little worried because in a room this large, there is quite a bit of reverb. And what Rafe and I have found is that when you're listening with speakers, and especially in a room with a lot of reverb, that it's harder to hear those underruns. So that's one reason why we personally prefer to listen for audio problems with headphones, or as you'll soon see, we actually like to look for them visually, too. So we heard the underruns. Let's look at them visually. I mentioned we were going to. Here's a long 15-millisecond underrun in the audio editor tool called Audacity.
Those long underruns are pretty easy to spot.
Yeah, but unfortunately, I wasn't just hearing those long ones. I was also hearing short clicks, and those were really hard to find with Audacity. Here's one here. This is only 64 frames, I believe, which is 1.5 milliseconds, I think, at, I don't know, either 44 or 48 kilohertz. And it took me a long time to find this one. I just didn't have the patience to keep looking for these.
Yeah, they're tricky to spot in the time domain, but in the frequency domain, underruns pop out. Here's that same area after a Fourier transform. See those spikes on the right? Those regularly spaced spikes mean trouble. You use frequency domain view, and then you can binary search to help zoom in on the shortest underruns.
So let's get back to my problem, my latency problem. I noticed that when I reduced buffer sizes, the latency went down, but I also was hearing these clicks.
So we were wrong. The buffers were just about as big as they had to be to keep the audio from glitching. They weren't just about saving power, they were also keeping it clean.
So now we needed to figure out why those glitches were happening. And while I was working on the system problem, it turned out Rafe had also collected some data of his own, which we're going to look at right now.
That's right. Isn't this beautiful? Maybe I should take a couple of minutes and explain what this plot is showing. What I was measuring is the start time and the end time of every OpenSL callback. This is by far the most useful information you can log. At first, I was doing this to profile how long my own code took to run, but I ended up learning a lot about how the system worked as well. So let's start with a little bit of background.
So we use OpenSL ES from Kronos Group, and in our implementation, the audio runs on a separate thread inside of your application process, and the thread runs in a tight little loop that looks a lot like a helix, like a spring. Each time through the loop, our OpenSL ES implementation will call your buffer completion callback handler to generate the next buffer.
The time between two successive callbacks is the cycle time.
And ideally, the cycle time should be consistent. In fact, it should be equal to the size of one buffer.
So in an ideal world, if we plotted the callback time against the expected callback time, we'd see a perfectly straight line. Of course, nothing is perfect. If we plot the time that callbacks actually arrive against the expected time of arrival, we're going to see some deviations. Each little squiggle in this graph represents a deviation from the ideal callback timing. But to tell the truth, I have a hard time using this graph to tell exactly how bad the deviation is. Instead, I like to view the data a little differently. Instead of looking at callback times, I just look at how early or late each callback arrived. Here, the y-axis is a measurement of deviation from ideal timing amplified so we can see it better. You can think of this as a measurement of the system's jitter. I've also changed the x-axis a bit. Instead of being measured in time, it's simply a count of how many callbacks have arrived. That way I can compare the jitter of two different systems, even if they have different callback cycle times.
OK, so now that we know how we're measuring and displaying this jitter, let's look at some real-world data.
Sure. So this is taken from a build of ice cream sandwich that's close to the one Glenn used.
It looks interesting, but why does it slope down and to the right?
That downward trend is actually the difference between, it's a difference in timing between the audio clock and the system clock. So let's look at the corrected version. Now, remember, an ideal system would show all zeros on the y-axis, meaning that every buffer completion callback had arrived exactly on time. Of course, no system is perfect. So what you'd expect to see in a good real-world system is a tight cluster of values right around the 0 mark.
It looks kind of like that. I mean, mostly, at least the green part.
Yeah, but you also see a lot of callbacks arriving 5 or 10 milliseconds late. That's manageable, even if it's not ideal.
But I don't like those red ones there, especially at the beginning, those outliers. They look like, what is it, 20, 30, 35 milliseconds late.
Dang, that's what those giant buffers were for, not just to save power, but to cover for the fact that the audio system was delivering some of these callbacks really late.
Now, this really bothered me, because Android is not a real-time system, but we had configured the thread priorities for audio to be nice level -19 for the system mixer, and then nice level -16 for application threads. And the scheduler really should not have been doing this. It just didn't make sense. Just to give you a background on nice values, basically, if this pi is all the available CPU time, then numerically lower nice values like -19 and -16 should get more of the CPU pi. And they should be scheduled on a regular cadence, not waiting tens of milliseconds, and certainly not 35.
Yeah, so those jitter outliers we saw in the previous slide, those are going to cause underruns. What was happening in the system to cause them?
That's exactly what I wanted to know. So I dug a lot deeper. Now, I'm not a Linux kernel expert, but I do have a background in real-time operating systems. I used to write real-time kernels. And so I felt very comfortable jumping in and doing some system measurements at the kernel level. At the time, we didn't have the systrace tool, which you may have heard of. And I didn't know about the existing Linux tools for tracing, like ftrace. So instead, I just built my own custom context switch tracer. This is what it looked like. Basically, every time there was a context switch, it would log information about this context switch into a ring buffer. The information was basically the next thread about to run and whatever was the current system monotonic time. Then what I would do is I would play audio, and at the same time, I'd run my context switch tracer. And whenever I heard a glitch, I would look and see what was happening in the system at the time of that glitch. And it took me a long, long time. But eventually, I found what looked to me to be the smoking gun. OK.
This is an excerpt of Glenn's context switch log. The first 12 lines are exactly what we want to see. The playback thread and the audio track thread wake up, do their thing, and then go back to sleep on a regular cadence. But those last 4 lines look wrong.
And by the way, this is real data. All the data you're seeing here today is real. This was the smoking gun. So let's look at that same data as a sequence diagram.
You can see the pattern here. First playback runs, then audio track runs, and then lather, rinse, and repeat. But what happens near the end of the trace? Right when the playback thread was supposed to wake up, another task gets scheduled instead. This is in spite of the fact that the audio has a higher priority, nice -19. How could that have happened?
Well, it all comes down to a Linux kernel module, which is called the Completely Fair Scheduler, or CFS. Earlier, I showed this slide showing nice values and the CPU pi. If you look really closely, there's a very important caveat there. It says, huge oversimplification. Nice values are not a quota system.
The CFS scheduler allocates CPU time fairly and proportionally to the nice level in the long term, but it does not guarantee wake-up time. In these two timing diagrams, the dark bars are the audio threads and the light bars are other threads. To CFS, the top and bottom diagrams are completely equivalent, but to an audio programmer, they're completely different. We want the pattern on top. So I tried working around CFS. CFS has a lot of tuning parameters. The most important one is the scheduling interval or scheduling quantum. There are other parameters such as how often it will check for fairness. And when I tuned those down to really small numbers, I was able to get rid of most of the audio underruns. But it turned out that all that messing around with CFS parameter used a lot more power, and even worse, it caused the overall system throughput for non-audio threads to go down because of excessive context switching. And worst of all, it didn't even solve my audio underrun problem completely. It just reduced the frequency. The most effective tweaks just reduce the time slice that each thread gets before the scheduler reevaluates. It doesn't change the core algorithm, which is to try to be fair to every thread. But in our case, we don't want to be fair. We want audio to go to the front of the line every time. Reducing the time slice just causes more context switching, which uses more power.
So from my real-time operating system background working on kernels, I knew about fixed priority scheduling. It's a very old concept, and I desperately wanted to use it. The basic idea is that you always run the highest priority ready-to-run task, no matter what. And if you assign your priorities correctly and appropriately, your system will work, no matter what.
In Linux, this means using a scheduling policy called SCHEDFIFO. A lot of audio developers know about SCHEDFIFO, and we know that there are plenty of Linux desktop programs that use it and Android apps that try. But it doesn't work in Android. On Ice Cream Sandwich, it did nothing. And in Jelly Bean, asking for SCHEDFIFO causes thread creation to fail.
That's because we disabled it for user mode threads.
Why did you do that?
Not me. Our system team was afraid of denial of service because basically one errant SCHEDFIFO thread could hog the CPU and take down the whole system. And yet we still needed our callbacks on time. So I went back to our system team and I tried to make another case for SCHEDFIFO. I showed them slides with numbers and statistics and power measurements. And this time they assigned me a buddy, a kernel expert named Dima, who you may run into today. He's here. Dima helped me navigate the issue and figure out how to mitigate the denial of service risk. The answer turned out to be based on a kernel feature that actually Google started working on several years ago in 2006 called control groups, or C groups.
C groups is a system for resource accounting. You can use it for all kinds of things, like setting CPU and memory quotas for different processes or charging for cloud servers by the CPU hour. In the case of Android, it lets us prevent audio threads from ever exceeding its CPU budget, and that mitigates the denial of service attack.
So in the end, the system team did agree we could run audio threads at a fixed priority if we used C groups to stay within the budget they gave us, which was a whopping 5% of the CPU. Later on, we got that budget increased, but actually starting with only 5% turned out to be a really good constraint for us. It forced us to reduce the CPU footprint of the audio system.
OK, keep that number in mind for later. For now, it's important to understand that SCHEDFIFO priority only applies to threads that are created by the audio system. You can't do it for your own threads. So that means if you want the lowest latency, you need to run your audio code on an audio thread. In practice, that means you need to do your processing in a buffer callback. That means writing your sound engine in C++ and using OpenSL ES. And of course, not doing your engine in Java means you don't have to worry about pauses from the garbage collector.
But you are still subject to the audio C group budget. We'll discuss budgets later on. But first, Rafe, show us some more numbers.
Sure. Let's see how well that change to SCHEDFIFO worked. This is a little misleading, but the build I measured contains some other fixes besides SCHEDFIFO, but it's essentially accurate. you can see that where ice cream sandwich jitter was all over the place, on Jelly Bean, it's clumped in a tight band right around 0. The problem is solved.
Woohoo! Well, not so fast. Remember that in order to get that reduction in jitter, we had agreed to a really tight budget for audio. At the time, only 5% of the CPU. Unfortunately, when I profiled the audio subsystem, on some devices it took longer than 5% just to run our mixer, our sample rate converter, and audio effects like reverb and EQ. And it looked like I had a massive optimization task in front of me because we had that 5% also for his application.
Now, to be fair, that subsystem is doing a lot of work, especially if effects are turned on. What was frustrating to me is that it was work that I didn't want. I'm not dependent on any one sample rate. I can do my own mixing. And I spent weeks with the signal analyzer determining the exact physical properties of that synthesizer's digital to analog converter hardware to build a precise emulation. I didn't want to add any one-size-fits-all effects on top of that.
My big aha moment was when I realized that pretty much every audio developer feels the same way. Every developer who's interested in low latency audio anyway. So instead of trying to optimize our system audio path, I just bypassed it. And I call this the fast path. Here's how it works. The top section basically is running under the old CFS scheduler. And that includes our normal mixer, normal tracks, which support resampling, they support mixing, they support effects, things like that. The bottom is the fast path, and here the low latency applications send their audio directly into the fast mixer, which then drives the hardware abstraction layer. And they all run under the SCHEDFIFO policy.
And they're limited to the audio budget of 5%?
Yeah, 5%. We're actually able to negotiate that up a little bit later, but there still is a budget. Now remember, earlier we were talking about power, and one of the reasons why buffers were so big was to reduce the CPU wake-up frequency. So when we use the low latency path, it does increase power consumption. Fortunately, one of our audio engineers, our audio tech lead, Eric, added another feature called the deep buffer path, which is used, for example, music playback, when your phone is in your pocket, and that is recommended when you're trying to conserve power instead of latency.
All right. So at this point in time, I'd been following Glenn's work pretty closely, and I was very excited to try out this new fast path. I'd just gotten a shiny new Nexus 4, so I flashed a build onto my device, loaded up my synthesizer, and nothing. No change.
No change?
Well, almost no change. There was some reduction in latency but nowhere nearly as much as I would have liked. Keep in mind, I'd already made all of the obvious changes. I'd rewritten my synthesis engine in C++. I was running in the OpenSL callback, so my code would run at that same high-priority scheduling. The obvious conclusion was that my app was to blame, so I started profiling. What I found surprised me a little bit. When I looked at my jitter measurements in the new build, they were terrible. I knew Glenn had measured much better jitter than this in his build, so I asked him what was going on.
I was really stumped, too, until I asked Rafe what sample rate he was using, and he said 44.1, which is what was used on the Nexus 7 and the Galaxy Nexus. But it turns out the Nexus 4 runs natively at 48 kilohertz.
So my buffers had to go through the sample rate converter, and the sample rate converter is not on the fast path.
Exactly.
Here's another plot that shows a related issue. This isn't as bad as the first one. There's only about a 5 millisecond variation in start time here. But there is something weird about it. The stripes in the data make me think I'm looking at some kind of periodic process, not just random noise. Let's zoom in and see if we can find a pattern.
Yeah, that looks like a pattern to me.
It's pretty regular. Looks like every 16 buffers, I get my callback late. It turns out this was because of another assumption I'd made that didn't hold true on the Nexus 4. I'd set my buffer size to 256, which was a convenient size.
What Rafe didn't know at the time was that on the Nexus 4, our native buffer size was 240 frames, not 256. And the greatest common divisor of those two is
16, right. So that's the next item on your to-do list. Adapt your buffer size and sample rate to match what the system is using. But how do you know what buffer size and sample rate to use? This is something next slide.
Yeah.
This is something that not only is there variation between devices, but it can change even across Android versions. In the early days, I struggled with this a lot.
So I asked Rafe what does he want in the next version of the Android audio platform, to better support apps. And the top of his list was an API to return this kind of information, native buffer size, native sample rate. And that shipped in API level 17. We'll give you a link to how to do that at the end of this talk.
Here's a snippet from my app showing how I use the new sample rate and buffer size properties to set up my synth engine. After I hooked it up, I found that my synth went from 8 voices to 20. Finally, I was beating the 30-year-old synthesizer I was trying to emulate. Now let's take a look at an Audible glitch that was really difficult to track down.
You're going to want to pay special attention to this, because even though we are going to be using Rafe's code as an example here today, we've seen similar issues to this throughout the audio platform and in other applications. And it's really hard to track down.
Here's a plot of the bug in action. What you're seeing is the start and end times of each buffer callback. The start time is blue, the end time is red. Most of the time, the start and end times are so close that you almost can't tell them apart. But what's happening at the beginning here? Let's zoom in and check it out. Here's a closer look. The callback started right on time, but the end time is way out there. It looks like the callback took about 16 milliseconds to process. That was enough to cause a dropout and skip a couple of buffers, which is why all of the subsequent callbacks are recorded as showing up 10 milliseconds late.
This time I didn't have an easy answer for Rafe, but we did have a new tool for investigating performance problems, systrace, and I knew that that would be good for investigating this problem. Systrace basically collects the same kind of data that I had been collecting with my manual homebrew context switch recorder, but it's much easier to use and has a really attractive user interface. We're going to show you a systrace first of some good audio playback and then a bad systrace. First, here's a systrace of audio playback working correctly. You're going to see every 5 milliseconds, the fast mixer thread is the one in red. It writes out a buffer of audio to the hardware, then it wakes up the audio track thread, which is part of the client, and that's the one in green, which is actually part of your application. And that's the thread that's generating the next buffer of audio. Then that computes beautiful FM sounds for a couple of milliseconds and queues its buffer, which goes to the fast mixer, and then it goes back to sleep for the next callback.
So around here, we see something else happening. The UI thread of the synthesizer, which is purple, wakes up and starts computing. But both the fast mixer and the audio track threads are higher priority. So when it's time for them to wake up, the scheduler suspends the UI thread and lets the high priority audio threads run. So that's good. No Audible glitch here.
But something still looks a little funny here. The audio track thread looks like it's been split in two.
Zooming in, we see our UI thread being scheduled, even though the audio thread should be higher priority. What's going on? Turns out that when that thread went to sleep, it was holding a mutex belonging to the allocator. Then when the audio callback went to allocate some memory, it tried to take the mutex and blocked. The only other thread to run is the UI thread, so the scheduler wakes it up, then it releases the mutex, and boom, the audio thread is runnable again. It's higher priority, so the scheduler bumps the UI thread and lets the audio thread run to completion, and we get our buffer to the mixer with plenty of time to spare. This time we were lucky.
This time. This wasn't our Audible glitch. But let's keep looking. So to help us out, I added a new systrace counter for us for audio called fReady, which basically is the number of frames that the application is providing to the audio mixer. You want that to always be high enough for the mixer to be able to read the next data from the application. And as you can see, most of the time it's 480, which is 2 buffers worth. But around 1.1 seconds into the systrace, we can see it dropping down to 0. That's definitely going to cause a glitch, no question. Systrace is a great tool for finding these kind of performance problems. It's much easier to see them than to listen for them. So we have a glitch. Let's zoom in and see if we can figure out exactly what's happening. At the arrow here, our user interface thread, UI, stops running, and it turns out it's holding a mutex for memory allocation. Then a whole bunch of other stuff runs, and looks like uEvent observer. Then the usual. Fast mixer wakes up, and that wakes up audio track. But at the arrow, the audio track tries to allocate some memory, and that's going to block. The UI thread was holding the mutex for the memory allocator.
OK, remember the last time this happened, the UI thread was the only thing ready to run. That's why we were so lucky. There was nothing else for the kernel to schedule. So the UI thread did its 30 microseconds worth of work and unblocked us. This time, we're not nearly as lucky because there's tons of other threads that want to run, and the scheduler isn't smart enough to realize that it needs to run the UI thread in order to unblock the audio thread. The fast mixer keeps waking up, but every time it does, there's no audio, we were blocked. So fready runs out, and we hear a glitch. It isn't until 11:41 milliseconds in this trace that the UI thread finally gets scheduled again, then releases the mutex, and the callback can run.
So this is known as classic priority inversion. Basically, it means that a high priority thread is being blocked by a lower priority thread that's holding a resource, such as a mutex. And some operating systems have special logic, especially in their mutexes, to handle this case, but Android is not using that feature.
Here's the funny thing. I know about priority inversions. I wrote my code very carefully. I didn't take any mutexes or allocate any memory, anything that could block. Yet the systrace clearly showed that the thread was blocking on a mutex. Tracing further, I found that the Sprintf call I was using to generate a log line was blocking.
Sprintf of all things.
Yep.
So turns out I ran into a similar issue when I was working on the audio fast path. I had a thread that was calling into another server by IPC, interprocess communication via binder. And I knew about classic mutex priority inversion. That's a well-known issue, but I didn't think about the risk of IPC.
There are a bunch of ways to deal with this problem, but for this kind of thing, the simplest is to use non-blocking techniques. Don't ever take a mutex in the audio callback, either explicitly or implicitly through things like memory allocation.
One really simple among the non-blocking techniques is way of avoiding blocking is single reader, single writer ring buffers. It's really easy to write, it's simple to understand, and it works really well for shuttling either small or large amounts of data between threads. It's commonly used in audio applications for this reason.
Here's how I used it in my app. The Java app puts its MIDI bytes into the ring buffer, then the C++ takes the bytes out. Checking how many bytes are available and reading them can both be done without blocking. If you weren't in a soft real-time context, you'd probably use a mutex for this instead. Do keep in mind, though, that you still need to use memory barriers, because ARM has a weakly ordered memory model. x86 has a total store order, so if you've implemented a ring buffer there, you may not be aware you need these barriers. If none of this makes sense to you, just use existing correct code.
And definitely don't call Sprintf. So let's see what your new graph looks like now that you've fixed your priority inversion.
You bet. Here it is. And here it is corrected for drift. Now it's looking clean. The outliers are gone as all of the code is strictly non-blocking. You do see some weird little ups and downs because of the power management system changing the clock frequency, but that's OK. Even at the lowest clock frequency, everything is happening under 2 milliseconds, which is properly quick. This might not seem like it looks better than the previous plots, but take a look at the scale.
That's a 1 and a 2. The start times are all clustered together the way we like them, but the end times are still a little bit weird. It looks like there's 2 bands. What's going on there?
My synth was doing its computation in blocks of 64 samples because it's convenient. Lots of other libraries do that too. Remember, the Nexus 4 buffer is 240 samples long, so sometimes we would compute 256, other times 192. That variation explains the 2 bands. This is a nice optimization, and it took my synth from about 20 to 30 voices of polyphony. After this, I took it the rest of the way with some old-fashioned cache optimization and SIMD magic. So now it's up to 64 voices. Between Glenn's work on the system and my optimizations in the synth engine, my DX7 app is starting to look pretty good.
This is where things stand for some devices. That's right, you knew there had to be a catch, because as soon as we started testing this design on a wider variety of devices, things started to get more complicated.
The core of what Glenn did is valid on every device, but each device has its own set of bugs, power management issues, driver bugs, or scheduling snafus. And each one of those has to be solved individually.
If you want to catch me during office hours, I'll tell you some war stories. So that's the last thing on my to-do list, is to work with our hardware partners to track down these crazy kernel, driver, and hardware issues that can affect audio performance. I'm committed to it, we're committed to it, but we're not there yet.
But we are moving in the right direction.
Yes, we are.
If you have some questions or would like to see more data, come see us in the Android office hours area right after this presentation.
We put together a website for all of you with a lot of good audio performance resources. So this QR code has a short link to it, and there's also the long link there if you prefer. It's code Google.com P and then high performance audio. Lots and lots of resources there, and we do plan on continuing to keep that website up to date with more things as we come across them. So thank you all for coming.
Yeah.
And again, please fill out the review forms, and let's talk at office hours.
See you there. Thank you.